It's great to be here again at this Sahd meeting for high-dimensional data. And actually thinking about high-dimensional data and data science problems, so convex optimization dates to the dawn of these fields where things like least squares permeating across every sub-branch. Lately, there is a renewed interest in convex optimization for, for reasons, acceptable by this community, things like new theory for convex models for sparsity and low rank, and the success of things like support vector machines. And, lately, things like array signal processing, medical imaging, things like recommendation systems are using convex optimization to solve interesting problems. But the renewed interest in convex optimization is putting the algorithms under immense pressure to accommodate higher and higher dimensional data sets. Moreover, we're interested in non-smooth problems, which typically make things a little bit more complicated as far as the optimization algorithms are concerned. And if you look at the convex optimization, the recent trend is usually we wanna find algorithms that have very cheap per iteration complexity so that they scale well. And fortunately, many of these applications only require low to medium accuracy solutions, so this is acceptable. It turns out that a large majority of optimization problems can be concisely summarized by the following template, convex optimization template, where we want to minimize a function f of x subject to a linear inclusion constraint such as ax minus b is in some convex set, and x belonging to some simple set, calligraphic x here. An example from an application that I really deeply care about, sparse recovery. For example, we would like to minimize the one norm of x subject to, let's say, some data constraint. A could be our data matrix, subsampled Fourier, or some feature matrix in machine learning where we say that the perturbations live in a radius of kappa. And then for signal recovery, we might say that the dynamic range of the signal is within some constant, right? So just to set up some notation, I'm going to talk, whenever I say f star, it'll mean the optimal value of this particular convex program. And obviously, x star needs to satisfy the constraints. Actually, so this needs to be minus in the convex set. While this looks like just related to the data set problems, it actually occurs naturally in the classical convex optimization setting too. If you think about the standard linear programming, semi-definite programming, second-order cone programming, they can all be written in this particular template. In many cases, you might have unconstrained problems, and in those cases, you can use a trick called splitting, and then you can reformulate it in this particular convex template, which gives you a unified perspective. And what's the benefit of this unified perspective is that if you have it in this particular fashion, then you can start applying, primal dual methods, which, the typical, the highlights of these methods is that typically the way we process and keep the data is in some sort of a decentralized manner, which is nice. Moreover, these methods have low per iteration costs, and you can do distributed computing. Right? Seems like it's a very important feature. And when you look at these methods, there's a lot of them, and some of them are reinvented, but many of them date, older than, they were invented before I was born. As opposed to going over all of this, I'm sure you heard about, ADMM, AMA, split Bregman, and so on and so forth. Let's talk about how, we can choose among this, zoo of algorithms. Now, if you think about it, when we use these algorithms, what we're doing is we're trying to come up with numerical solutions. And one way to prefer one algorithm over another one is to figure out how long it would take us to obtain, let's say, an epsilon approximate numerical solution, right? So let's just denote an epsilon approximate solution as x star epsilon. And a simple metric is what's the time to reach that epsilon. Now we can just simply write, the time to reach the epsilon would be the number of iterations to reach epsilon and the per iteration time of an algorithm. Simple enough. Right? And when we think about many of these primal dual methods, there's this subclass called first order primal dual methods, which are characterized by the oracles they use from the objective function. In this case, these first order methods basically use A and A transform and some appropriate proximal operators. And I'll tell you the definition of the proximal. Anybody heard of proximal operator? Okay. So I'll tell you the definition a little bit. The only issue that is somewhat major in this particular realm is, the number of iterations to reach epsilon. The reason is that, somehow the epsilon accuracy is elusive when you look at the constrained problems. And let me expand on this a little bit. So if you were to do unconstrained minimization problem, and the problem is convex, we already know that, any x is feasible. You're allowed to pick any x, and you can't really beat this objective value, f star. Any approximate solution needs to be basically bigger than the optimal solution, objective value, right? But when you go for these constrained problems, you can easily find epsilon accurate solutions that has smaller objective value. And that is mainly caused by the fact that when you talk about epsilon accuracy, unless the epsilon accurate solution is exactly feasible, if it is exactly feasible, it has to satisfy this. But typically, the way we operate with A transpose, and the proximal operators, the iterates are not exactly feasible, and you can easily find epsilon accurate solutions that have smaller objective value. So what we're going to care about now is somewhat of a different notion of epsilon accuracy. So what we're going to say is that a point is epsilon accurate if, let's say, it satisfies this, right? So x star minus f star is less than or equal to epsilon. You can actually put absolute value here, right? And then we're going to say that they're also epsilon feasible. So we're going to try to control how much they deviate from the constraint set. And we're going to assume that this x star epsilon is exactly feasible for some simple sets, let's say box constraints. All right. And if the problem is a unique solution, we can also talk about epsilon accuracy for your distance to the optimal solution, x star, which is unique. And of course, the epsilon can be different for the objective residual or the feasibility gap or the iterates. Right? Not a problem. And when you think about these kind of epsilon accuracy, finding the fastest algorithm becomes a little bit vague in the sense that you have all kinds of algorithms, things like ADMM, having penalty parameters that are not clear how to choose. You have primal dual first order methods that have gap-based characterizations with constants that are just infinity that they beat with certain rates. And many of them start assuming certain structures on the convex template that do not hold in practice, like strong convexity or Lipschitz gradient, that are not necessarily what we have in a given problem. Now, on this front, we've done some work that has some precise characterizations and explain how ADMM, AMA work using first order information, things like A transpose and proximal operator, but that's not what this talk is about. What we're going to try to do is we're going to talk about optimal methods with even cheaper per iteration costs. So what we're going to try to do is we're going to try to get rid of proximal operators. All right. Now, if you look at the last 2 decades of work in data sciences, one thing people have realized is that even if the problem is non-smooth, you can solve it as efficiently as if it is smooth if the proximal operator is efficient. What is the proximal operator? So let's say we have a convex function G. The proximal operator, I'm abusing a bit of notation, so think of this X as the p-dimensional. So you want to minimize G of Z plus a quadratic term. This is the basic definition of the proximal operator. You're looking at the argument of this. And this thing is actually quite efficient for a lot of the problems we're interested in. Let's say you want to minimize the L1 norm. You use the proximal operator of the L1 norm, and it corresponds to soft thresholding. It's just coordinate-wise operation that just looks at the coordinates and thresholds them by some constant. Now, if you look at cases, I mean, it's perfectly valid to assume that this thing is efficient, and then you have access to all kinds of algorithms that you can use to solve, obtain numerical approximations of the convex template. But I want to give you one example, which is the nuclear norm. So let's say you're interested in a function minimizing the nuclear norm, and you would like to use any of these algorithms. In this case, the proximal operator is the nuclear norm plus this quadratic term. It has a unique solution. The only issue is that the proximal operator is not decomposable in the sense that you can't really go over the coordinates and then threshold. What you need to do is you need to use a singular value decomposition. And if the problem dimensions are large, then the singular value decomposition basically kills you for higher and higher dimensional problems. And it practically rules out all the proximal primal dual first order methods, basically, if you're interested in, let's say, minimizing the nuclear norm subject to a linear inclusion constraint. So the key question is, can we avoid the proximal operator for something cheaper as a building block? And of course, there's precedence to this. And the earliest example is the Frank-Wolf method, which actually works with a much restricted template. So let me tell you what this problem is. So you're interested in minimizing an f of x, but now f of x is not just general f of convex x, but something with a Lipschitz gradient. Let's say it's smooth. And there is no inclusion constraint. We have some sort of a simple set constraint. Right? What the Frank-Wolf method does is also called the conditional gradient descent method. Martin Yagi has a very nice review in ICML. What it does is it linearizes the objective, and it optimizes the so-called linear oracle at a given iterate xk, subject to the set. Typically, this is easier to solve than the proximal operator. I'll tell you in the next slide how. And it just weighs the average, averages the solutions of this. And actually, if you think about the nuclear norm, so suppose the set is the nuclear norm is less than or equal to a constant, this just corresponds to finding the the principal singular vectors of the input. It would actually just correspond to finding the principal singular vectors of this gradient, which is nice. And the cool thing about this is that in many cases, you don't even need to form the gradient. You can just realize that if you need to find the principal vectors, you can use some of these power method tricks to do this very efficiently. So it saves you space and computation. So what we're going to do is we're going to generalize this. This generalization has been, it's been around. So what we're going to do is we're going to think about the minimum of g of z minus this inner product subject to this constraint. Typically, people working with Fenchel conjugates will recognize that, oh, hi, this is just the Fenchel conjugate. But we're not going to be interested in the value of this Fenchel conjugate, but rather the argument of the Fenchel conjugate this time. Okay? So when g is 0 here, this is the linear minimization oracle used by Frank-Wolf. When there's no domain constraint, this is basically the derivative of the Fenchel conjugate of g. Right? And we're going to call this the sharp operator. Right? I mean, the naming comes from Yuri Nesterov. And I've been talking about this for a while. Nobody resisted this name, so simply we're going to call this sharp operator. And let's take a look at this sharp operator. I'm going to give you two examples. One example is the one that I just mentioned. So let's say the g of x, sorry about this, but g of x is just 0. Let's say this constraint set is the nuclear norm constraint. Then this is just finding the principal singular vectors. Let's say there's no constraint, but g is the nuclear norm squared. not the nuclear norm, but nuclear norm squared. You can actually do any power of nuclear norm. Then the sharp operator corresponds to, again, finding the top singular vectors weighted by the spectral norm of X. Right? If you think about it, they have pretty much the same computational complexity. Now, given this understanding, if you look at the conditional gradient method or the Frank-Wolf method, what the Frank-Wolf method does is here, this is the sharp operator with respect to the set, and you can actually see the generalizations of the conditional gradient method called the generalized conditional gradient method that actually works with the composite form f of x plus g of x, where as opposed to minimizing this, you have g of x plus the great linearized form of the objective. And this is basically the sharp operator for this g. Right? Is this clear? Too early for this? But if you notice, in this problem template, we don't have linear inclusion constraints. And from the theoretical perspective, we actually know that the conditional gradient method cannot work for non-smooth objectives. So if you think about it, if f was non-smooth, then we couldn't have used this method. Or in the composite case, if f of x plus g of x, they're both non-smooth, you cannot use the generalized conditional gradient method. So what we're going to do is we're going to show you how to do this now. All right. So for the sake of simplicity, I'm going to assume that we don't have a general inclusion constraint, but ax is equal to b. At the end of the talk, I will tell you how to handle this generalization with the inclusion. So here's the plausible algorithmic strategy. So given this convex optimization problem, if you look at the KKT conditions and so on and so forth, there's a natural minimax formulation that goes through the Lagrange function. So let's define the Lagrangian of this problem. We have a Lagrangian function with respect to the primal variable x and the dual variable lambda. And the Lagrangian is basically f of x plus this Lagrange parameter inner product with the constraint set. So if you think about this minimax problem, think about minimizing the Lagrangian with respect to x. Let's call this solution x asterisk, not x star. X star is the solution of the original primal problem. And then for any given lambda, you can parameterize the solution. If you take this and plug it back into the Lagrangian, then you have something called a dual function. And you think about this problem, then for any given lambda, you find this x asterisk, you plug this in, you maximize the dual function, you have the dual optimal. Right? Now, the cool thing about this is that the dual function is concave, so maximizing this dual function is basically a convex optimization problem. And given the dual optimal, you can plug this back in here and you can find x star. Right? So what we can do is, given this observations, we can say that, okay, so let's try to make some progress finding the dual optimal and somehow construct a primal solution in the meanwhile. Now, what are the challenges to this strategy? Well, is this correct? It's a basic challenge that you should always think about. The second thing is the efficiency of making progress in the dual function, right? And third is this mapping between the dual and the primal. Seems like tough, right? Now, establishing correctness, let's just get that out of the way. If you assume f is proper and the Slater's conditions hold, this strategy is a good one. So let's just scratch that. So let's then think about the computational efficiency for the dual problem. Now, when you look at this dual function, I said it's concave, so the standard convex optimization algorithms apply. So let's assume that the dual function is bounded subgradients. Right, so here is the subgradient of the dual. Let's say it's bounded. If you have this particular assumption, which holds in many cases, then you have the subgradient method with the worst case iteration complexity of 1 over epsilon squared. Right? Well, if the dual function has Lipschitz gradient, Right? So what that means is that you look at the gradients of the dual function, you look at the differences, then the difference is bounded by a constant times the differences of the points you evaluate the dual function. Then this is great, because then you can use the accelerated gradient descent method. Your iteration complexity would be 1 over square root of epsilon. Right? Fine. But so when can the dual function have Lipschitz gradient? Well, if the function, the original f of x is strongly convex, this is satisfied. But in general, it's not, so you're basically in this setting. So what we're going to do is we're going to assume something in between. Right? We're going to assume that the dual function is Hölder continuous for some constant nu between 0 and 1. And the definition of the Hölder continuity is basically you look at the gradients, and then you look at the supremum of this by taking a ratio between the gradients and the differences of the points to the power nu. Right? So let's assume that there exists a constant m nu, which is not infinite. So if you have this assumption, for nu is equal to 0, you're in this. For nu is equal to 1, you're here. For nu anything else, you're in between, basically. Right? In this case, the dual problem is Hölder continuous. OK, then what we can do is use a universal gradient descent method with some complexity. All right. So just to set up, just to make the connection with the convex optimization, so let's consider this convex minimization problem. We say that this G has Hölder continuity if this is satisfied, and nu is equal to 0 corresponds to the bounded gradients. Nu is equal to 1 is the Lipschitz gradient. Now, for this class, there is actually a lower bound in terms of the per iteration complexity. And it's a complicated function of nu, right? But it covers the basic cases that I just mentioned. So for nu is equal to 0, you get the 1 over epsilon bar squared. If nu is 1, that's the square root of epsilon bar. All right. Now, so how do we come up with a method in this setting? The Hölder continuity gives you a basic majorization function. And the majorizing function deceptively looks like the quadratic majorizer, except that it's not quadratic. So given the Hölder gradient assumption, what we can do is we can bound the function g by, again, a linearization plus m nu divided by 1 plus nu x minus y to 1 plus nu. Right? We can basically try majorization minimization algorithms, but the issue here is that in many cases you have no idea what nu is and no idea what m nu is. If you knew, then you would have just used either, let's say, the subgradient method or the accelerated gradient method. Right. So given the structure Yuri suggested last year is that we can actually summarize this bound in a non-adaptive fashion by a quadratic plus an inexact term. So given this bound, suppose we don't know what m nu is, but what nu is, it wouldn't matter. There exists an m constant and an inexactness parameter delta such that you can just replace this by a quadratic plus an inexactness. Right? So you can approximate this majorizing bound. But still, these depend on these unknown parameters. And it turns out that you can adapt to these unknown parameters by a simple line source strategy. And this is the remarkable part of Yuri's paper, is that in practice, it turns out that you don't need to know what m nu is or nu is if you're willing to do a couple of line search steps and just check if this inexactness parameter is satisfied with the step sizes that you get out of the line search. So what he did is he proposed this universal gradient descent method. And what it does is it just works like the standard gradient descent method. It gets some gradient from the objective, or subgradient, so a little bit of an abuse of notation here. It does a line search to ensure that this inexactness level is satisfied, and he ties this inexactness level to the original inexactness of the primal problem. Right? So you say, I want to find an epsilon accurate solution for my original problem. Then he just keeps this epsilon It just does this line search at every iteration. And then it's interesting that you get a universal method because it ensures the best rate of convergence for any new and unknown constant m nu. That is very important. And yes, there is an accelerated version, but it is somewhat very complicated, right? Well, in this domain, what we've done is, of course, nothing too new, but we came up with a simpler version that is easier to implement based on the FISTA idea. But that's not the new, that's not the intellectually new thing about the primal dual setting. If you look at Urey's algorithms, none of them are applicable to this primal dual template. So thinking about the primal dual template, this is what we do. So think about the sharp operator. Here, I just recall the definition. You pick a level of inexactness that you want to solve for this original primal problem. If you were to apply the dual gradient, you again, so if you apply this primal dual method, you make progress with the dual using just the standard dual method with line search, and you have an inexactness parameter epsilon. And if you were to do our method with the FISTA variant, which is basically 3 lines, you have a weight update on tk. Tk is something like k. It scales with k. You have the standard acceleration step, and then you have the gradient update step with the line search. But the line search steps basically require higher and higher precision as the iterations go along. So think of tk as k. So per iteration, your inexactness for your line search needs to be more precise as you go along. And now what we've shown is that you can actually construct primal iterates using the sharp operators. So here, but the averaging basically depends on the local Hölder constants that you get out of the line search. And it's not like the Frank-Wolf method where you have a non-adaptive weighting of the iterates. So here you take the iterates, you weigh them by the inverse of the Hölder constant. This is for the gradient method. And for the accelerated gradient method, you weigh the later iterates higher because they're weighted by the ti here. And then you again average them. So overall, what we managed to do is, so you take we apply the dual method to make progress in the dual. We use averaging to obtain primal iterates, and then we were able to show these kind of guarantees for the primal and the feasibility of the iterates. And this is basically great. So for the gradient method, if you use it on the dual, you get this kind of a convergence rate. And if you were to do the accelerated gradient, well, accelerated method in the dual, accelerated gradient ascent in that case, and then do the averaging where you weigh the later iterates higher, then you have this kind of a convergence. I mean, the expressions look complicated, so let's just summarize them, okay? So if you summarize them, it turns out that we have a primal dual method that just uses sharp operators in the dual function, does weighting in a particular manner in the primal function. So if you want to get an epsilon accurate solution for the objective and the feasibility, then you have some scaling, right? But given the lower bound, it turns out that the accelerated, so if you were to just use this gradient method, 2 minutes, okay. Wow, I went very slow. Then it's optimal for nu is equal to 0, which is not so bad, right? But if you were to do accelerated method, it's optimal for all nu with this inexactness. All right. So let's just give some examples. So this is a matrix completion problem where you want to minimize some observed entries in a matrix with the nuclear norm constraint. This is a standard thing in machine learning. What we're going to do is we're going to not do this, but basically come up with a robust version with one norm on the error. Right? So this is a problem that Frank-Wolf cannot solve. And you can apply the methods, and it turns out that the accelerated method actually, with similar complexity to Frank-Wolf, quickly converges. Well, due to lack of time, I'm going to just skip this. So if you want to handle constraints such as this one, all it requires you to add the proximal operator in the dual. This is not too terrible because you work in a smaller dimension. And what is interesting is that in this setting, you can actually minimize the nuclear norm subject to, let's say, some robust errors with this method. Nothing changes in the primal dual setting. And when you do that, actually, you come up with, let's say, some normalized mean absolute error criterion. And then the accelerated method really reaches that and actually improves this generalization or test errors. So it's just a matter of writing how you want to set up the problem. Anyway, so we apply these ideas to things like phase lift and solve really huge dimensional phase lift problems using convex methods. I mean, if people are interested in the phase lift problem, we can talk offline. The point about this is that we have a way of actually tuning the Frank-Wolf for the phase lift problem using the data, so we can actually apply Frank-Wolf. And the point about this is that you never form a gradient. You always work with rank 1 matrices to come up with a solution to the phase lift problem. And you can take large images and recover them perfectly with convex methods. Typically, people use non-convex methods to solve this just because the problem is huge, right? The same thing, you can do this for HD images. It just takes a very few iterations. And the point about the accelerated method is that if you look at the Frank-Wolf method, you require just fewer iterations, and the time complexity is much better than Frank-Wolf. All right. You can do bigger dimensional problems with millions of variables and so on and so forth. Right. So let's conclude. Otherwise, my chair is going to kick me. So what we've done is we've looked at this general primal dual template and basically showed how to solve these things with optimal rates using the so-called sharp operators. So it just gives you a little bit of a different perspective in terms of problems that you're interested in. That is, if you want to solve the problem and the proximal operator is nice, that's great, you should use it. But if the proximal operator is very expensive, there's an alternative with the sharp methods. And this primal dual framework is very flexible and uses the sharp operators and gets you, optimal rates and per iteration complexity. With that, I'll thank. The rest is just citations.
Okay, questions?
It's very clear, huh?
So I got a question. When you're reconstructing those images at the end, you're reconstructing them from random observations, or what do you?
You mean the phase lift images? These are random coded.
So you're just giving me random samples of the phase of Fourier transform.
This is the setup Emmanuel Candes has with this diffraction patterns, design diffraction patterns.
Okay.
So we use their setting. They have this Werthinger flow algorithm, which is non-convex. And with the Werthinger flow, if they have this coded random patterns, they give some guarantees. We just realized that if you have these, you can already run the convex algorithms, which are a little bit more robust in terms of the noise. I mean, for their settings, the convex method does not take much longer than the non-convex method.
Thanks.
No problem.
We should probably move on since we ran over, but thanks.
Thank you.